So it gives me absolute pleasure to shift a little bit away from COVID and introduce to you Dr. Patrick Pilarski. The kind of work that Patrick does is really exciting, and I thought it was important for people in the department to hear about it. So Patrick is an associate professor in the Division of Physical Medicine and Rehab. He holds a Canada Research Chair in Machine Intelligence for Rehabilitation at the University of Alberta. He's a fellow of the Alberta Machine Intelligence Institute, or AMI, and principal investigator with the Reinforcement Learning and Artificial Intelligence Laboratory. He received his bachelor's degree in electrical engineering from the University of British Columbia in 2004, and then did his PhD in electrical and computer engineering at the University of Alberta in 2009. He completed his postdoc training in computing science with Dr. Richard Sutton at the University of Alberta. Patrick's major research interests include reinforcement learning, real-time machine learning, human-machine interaction, rehabilitation technology, and assistive robotics. He leads the AMI Adaptive Prosthetics Program, an interdisciplinary initiative focused on creating intelligent artificial limbs to restore and extend abilities for people with amputations. What I thought was really fascinating from a departmental point of view is also his interest in other areas of artificial learning. So he's pioneered techniques for rapid cancer and pathogen screening through work on biomedical pattern recognition, robotic micromanipulation of medical samples, and handheld diagnostic devices. Patrick has authored or co-authored more than 90 peer-reviewed articles and is a senior member of the IEEE and is supported by provincial, national, and international research grants. So without further ado, I'll let Patrick take over from there.
Great. Good morning, folks. I am just going to start my slide sharing properly here, and then we can begin. Hopefully you can all see me and hear me. I'm assuming that that's the case, and Andrew would tell me otherwise. So welcome to my, thank you. That's fantastic. So welcome to my basement, the place where I've spent the last 7.5 months of working since we mostly went to work from home. Today, I'm going to share with you a topic that I'm very excited about. It is the topic of artificial intelligence in medicine. And what I'm hoping to do, and I'll get to learning objectives in a second, what I'm really hoping to do is to share with you a few definitions so you can ground your thinking in this area, some of the implications of radical transformative change that we're starting to see in the field of artificial intelligence for the field of medicine, and to be able to think about some of the future impact that these transformations will have. The obligatory COI disclosures. I'm not affiliated with any medical device companies or organizations. I am a senior staff research scientist with a company called DeepMind, a fundamental AI research company, an office co-lead here in Edmonton, and also the vice board chair of the Alberta Machine Intelligence Institute. So I did say I'd get to learning objectives. I promised that, and I'll deliver. The first thing I really want this to be, maybe the main take home you get from the talk, is that you should be able to go out and someday when we can socialize again at a cocktail party, be able to define AI, be able to define machine learning and related fields from the concepts in the field of machine intelligence. This is what I really hope that you'll be able to do, and in particular, be able to describe some of their defining characteristics. As a secondary goal, I'm really hoping you come away from this with the ability to discuss in one way or another how AI has been applied to medicine. And I'm going to specifically focus on physical medicine rehabilitation. That's the division I'm based in, and I'll ground most of my talk in that area, but I hope you're able to extend this to other areas of medicine. The next set here is that I'm really hoping as well, I promised future implications and future impact. I'm hoping this will help you estimate the way that these changes in the field of intelligent systems will actually have an impact on you in the next 5 to 10 years. This is always that weird squishy time frame where people have great trouble estimating. But I'm hoping that this talk will give you better evidence and better resources to be able to estimate how these changes in other fields, especially fields of artificial intelligence and advanced computing, will impact your own study, your work, and your practice in your life in the next 5 to 10 years. So with that in mind, I'm going to jump to a rapid fire series of videos because I like videos, especially at 8 o'clock in the morning. And the first is what I think is an example of some very transformative and groundbreaking science and medicine. This is a study participant, Jan Schuurman, down at the University of Pittsburgh, working with the BrainGate project. And what I want to note here is that Jan is unable to move her body from the neck down. So Jan can't move her arms and her legs, but at the same time, Jan is now actually able to control a robot arm to begin to feed herself a chocolate bar, to eat silly strings, to fist bump a doctor, to sort shapes, and to engage in the world around her. Jan has direct brain implants. So Jan has electrode arrays that are implanted into the surface of her brain that allow her to essentially pilot this robot arm to extend her abilities out into the world around her. I think this is really miraculous. And so I wanted to start our discussion today with this idea from brain-computer interfaces and this transformative example. It's not the only example. So we think of other people that are working on not just interfacing with the human brain, but in fact, some cases trying to replace parts of the human brain that have been damaged. There's work by Theodore Berger and others that are trying to find ways to use advanced computing technologies to, in fact, model regions of the brain that might have been damaged, and then replace damaged tissue with hardware and software that replicate its functions. Think of long-term memory consolidation. This is one of the examples I'm actually citing here. And I do want to note that I've put very detailed references at the bottom of every slide. That's not just to be thorough, but it's to provide what I promised, which is provide you with resources to follow up on topics that you find exciting after this talk. So the idea might be that you know, if a part of the brain that helps with long-term memory consolidation is damaged, that part could be well modeled, that it could be, in fact, replaced with a piece of technology, a chip, that allows people to continue to do what they did before, but without that piece of missing brain tissue. Moving to more towards the peripheral nervous system, I think many of you are familiar with some of these particular examples. This one's from Johns Hopkins APL, but the idea that we might begin to not just rewire the human nervous system, but build technologies, build robotic technologies, electromechanical technologies that allow someone, say with an amputation, even a shoulder disarticulation, to begin to interact with the world again. And if my next video, yeah, good, we're sparking it back up here. And that in recent years, in fact, that these kind of technologies are not just affixed loosely to the body, but they're now beginning to be integrated directly into the bone structure of the body, that we now see assistive technologies integrating with the bones, with the peripheral nervous system, such that a person and their technology are tightly or intimately coupled. I'm going to come back to that theme later in the talk, but for now, I'd like to continue our whirlwind tour through transformative technologies. And the next one that I'd like to highlight is, in fact, functional electrical stimulation. So earlier we saw Jan Schuerman interacting with a robot arm by way of implants directly in her brain. Those same implants that might be embedded within different regions of the cortical tissue could also be used to effectively pilot a body which is no longer under the control of the user. The idea that you might almost create a synthetic nervous system, another series of wires that run in parallel with those no longer under an individual's control, and that through direct volitional intent, through the use of the mind and the will, that person could in fact pilot or move their own body by stimulating the muscles and the nerves, and receive feedback from that body by way of those same channels. This is another really exciting area of study that we're just starting to see reach new potentials and new heights. I've mentioned a lot about wires. You've seen wires in almost every one of my slides so far in one way or another. We're not limited to wires. Technology is also being implanted within the body, within the muscles of the body, or within the deeper tissues, such that it can wirelessly connect to itself and outside of the body. This could be used for the control of devices or for monitoring and recording things that are happening inside the body. So we're starting to see devices not just attached by wires, it's a box with wires that goes under the skin or through the skin or into the brain, but we're starting to see devices now that are embedded throughout the body. Devices maybe the size of a grain of rice, maybe bigger, that are able to both give input to the human body and also record from the human body. Moving farther out in terms of invasiveness, we also see now technology beginning to interact with people in the way that they move and the way that they locomote through the world. I'm giving one example from Jose de la Milan and the EPFL folks, but this is a brain-controlled wheelchair where the person and a wheelchair were interacting together to navigate the world around them. So the person was in control of the wheelchair, but the wheelchair was actually using things like computer vision and other advanced computing technologies to be able to navigate that world well with minimal effort on the part of the user that was controlling or piloting the wheelchair. Okay. Moving on to wearable devices. A lot of the examples I've shown you so far were all research devices. These were things that you might find in a lab. These were things that you might have seen mostly in the realm of scientific papers. We're now starting to see that, in fact, some of these advanced technologies are being deployed in a clinical and a commercial sense. Pattern recognition, a way for artificial limbs to essentially divine the intent of the user and perform the right motions, are now starting to see commercial use and widespread deployment. And more so, you could go to one of the big box stores. I guess people used to go to big box stores. Maybe we still go out and shop for things occasionally and don't just have them ordered to our houses. But back in the day when we drove these mechanical boxes with wheels to big box stores, you could have gone out and actually bought brain body machine interface hardware for very little. You could buy it for a couple $100 and be able to pick up something that records signals from your muscles, or even records, in a very crude way, information directly from your brain. So what used to be very expensive medical technologies that were only deployed in clinics or in research labs are now something that any person in the world can arguably buy off the shelf with a little bit of effort or a little bit of money. This is we're seeing a transformation, a step change in the access people have to brain body machine technologies. Okay, so why did I show you all of this? I mean, I like seeing videos in the morning. I like talking about cool technology, but I showed you all of this for a reason. And the reason is that in one way or another, all of the examples I just showed you, from devices directly interacting with the tissue of the central nervous system, to the peripheral nervous system, to the muscles, to the bones, that these devices, in one way or another, all involve machine learning or machine intelligence. They all involve intelligent systems to create a mapping between a person, their intent, and the devices that are impacting them or assisting them in their day-to-day life. Even those like $200 armbands you could buy from a big box store are using machine learning to interpret the patterns coming from the human body, and in one way or another map those to even how you might control a presentation or controlling a remote control car. So this gets me really to the big picture point of the talk, which is that machine intelligence is now becoming the glue. It's becoming the foundational technology that connects the human body to assistive machines that are aiming to augment or support the person in what they do in their daily life. So we're going to focus again on physiatry for the next little bit of the talk, but I really do want to zoom out later on, and I'll show you how this is bigger than just a person, say, connecting to an artificial limb. Right, this is the main glue. The machine intelligence is the glue that is beginning to connect all of the signals flowing to and from the human body and the human mind to all of those signals that are flowing to and from the machines that assist us in our daily life and augment our ability to live that daily life and to do the tasks we do. So before we even talk about machine intelligence and things, we really should define things. And this is, I think, one of the aspects of the field of artificial intelligence that is often left behind, is that people forget to try to actually define what it is to say something is related to artificial intelligence. So to do that, let's actually define intelligence. And we're going to define this based on the views of John McCarthy. So John McCarthy coined the term AI, artificial intelligence, in 1955. And McCarthy's definition of intelligence is still one of the most satisfying to me and one of the most compelling that I've heard so far, which is that intelligence is the computational part of the ability to achieve goals in the world. So for those who are familiar with Mars tri-level hypothesis, the idea that you might have computation, the algorithms, and the way that things are actually implemented, intelligence is the computational part of the ability to achieve goals in the world. So then with this in mind, his definition of artificial intelligence is actually fairly straightforward. It is making the science and engineering behind making intelligent machines, and especially intelligent computer programs. And so if we put those two things together, we see that artificial intelligence can be well and clearly defined as the science and engineering of making machines and computer programs that manifest the computational part of the ability to achieve goals in the world. So that is a great definition, but I'd like to zoom into, if for those of you that are birders in the audience, go out bird watching, what are the field marks? Like if you see intelligence running around in the wild, what are the things that really pop out for you? What are the things that allow you to say, yeah, that's intelligence? Now, normally, if I were giving this seminar live, I'd be picking on folks in the audience and saying, tell me what you think is a hallmark of intelligence. And we'd have a discussion and an engaged debate about that before we move on to the next bit. It's a little bit more tricky with this webinar format. So I am going to move on to my next slide and sort of spoil the punchline of this and say that for the purpose of this talk, and especially in my mind, for the purposes of thinking hard about how artificial intelligence and intelligent systems can be applied in medicine, I try to boil down the hallmarks of intelligence to data, decisions, and goals. And you can see in my slide here that these really, in my mind, dovetail together. But I find that these three building blocks allow for very clear thinking and clear discussion regarding a technology that embodies the aspects of intelligence and uses those to in some way support humans in their daily life. So data, obviously the things that are flowing from the world, goals, the things that are hoping to be achieved, and the decisions that are made to integrate data with goals. There are many sort of principles that flow through this pathway from data through decisions to goals. Many of you, some of you I know I've already seen in the participants list have heard me talk about this before, that I believe this to flow into three main paths. And there are many ways you could slice this. Again, for today's discussion, I'm going to ask you to humor me and think about the hallmarks of intelligence in terms of perception, prediction, and action. Perception, how a machine is able to view, to take in observations from the world, to take in the information that's flowing in. Prediction, how it can use that perceptual stream to begin to forecast how the future will unfold, to capture the core patterns or the core regularities of the information in the world. And then action, how it uses that perception and those facts or those principles that it is learned to begin to act upon the world. Now, if you're in a different field, if you were computing scientists, most of you are computing scientists, I might call this representation, prediction, and control. If we were talking about the fundamentals of science, we might think about being able to observe and explain a phenomena, to predict it and then to control it. There's many, many compatible ways of slicing this. For today, I'd like to think about perception, prediction, and action in service of the pathway from data through decisions to goals. Okay, so we're gonna play a fun game. And so again, we can't do this in person, but I'd like all of you sitting in front of your computer monitors, wherever you are, I'm gonna show you a bunch of things. And then you have to just think to yourself, intelligent or not? Just like, it's really a binary decision-making problem. So I'd like you to do this. We're gonna go rapid fire through a couple of these slides. So first, intelligent or not? A toaster. I'm picturing all of you going like this or like this in your home studies or in your offices. Okay. A vacuum cleaner, a Roomba, an intelligent vacuum cleaner, perhaps. We don't know. This is thumbs up, thumbs down. Bumps into walls, vacuums. Okay, good. Ooh, one of these things, those smart speakers. You can talk to them. You can ask them to order you things online or to play music for you. This, probably not. Arguably not. Probably not. A robot, a small robot that can pick up objects, put them in a trash can, can tell you the 3 laws of robotics, can locomote, and can speak multiple languages. Okay, cool. I hope you all did that exercise at home. Again, it's very hard for me to know, but I'm gonna give you the benefit of the doubt that you all participated actively. And I did that exercise because I want to next address some of what I think of the common misconceptions. I think McCarthy would agree were the common misconceptions about intelligence. And the first is really this: that intelligence is a single line on the whole possible space of ways that a system might behave, and that there's things that aren't intelligent and things that are. That it's this A/B test, like the game I just made you play. That in fact that something is either intelligent or it is not. I think this is a very dangerous misconception, especially when we try to make reasoned judgments about how intelligent systems technology might be applied in medicine. So if we don't buy that this is a binary distinction, then the next thing that people usually do, and we've seen this over the history of technology, is that things get separated into what amounts to appliances and AI. Things that become commonplace, things that like a toaster that actually has a thermostat in it so it doesn't burn your toast, or a robot vacuum cleaner that will bump around your house and make sure to clear every nook and cranny. They become so commonplace that what in the 1950s or 60s would have been evidence of like strong machine intelligence, this is artificial intelligence at its core, now just become appliances. The smart speakers are sort of on the edge of this. They interpret our speech, but at the same time, they're becoming so commonplace that people start to demystify them. They start to think that the magic is gone and treat them as appliances. Robots walking around are still perhaps foreign enough and still so removed from our usual day-to-day that people immediately jump to saying, whoa, that's AI. That is 100% artificial intelligence, but not that robot vacuum cleaner. That thing, I see it every day. And I think all of those are interesting discussions, but they all miss the point in that, to go back to McCarthy's definition and to think really hard about intelligence as a continuum with respect to what data is being used, what decisions are being made, and what goals are being achieved in terms of the way that a machine perceives the world or begins to build up knowledge or forecast the world or takes action upon the world in service of its goals, that intelligence has many, it's a continuum. It's a very detailed continuum. Does the toaster do a better job of monitoring toast, perceiving the temperature of toast and then not burning it than I do? Yeah, it really does. Does a smart speaker, is it able to process more languages than I can? Can it do 15, 20, 100 languages and I can only do a very small handful of them? Handful or even less if you don't count math. I think that the intelligence that we start to perceive in our systems is very well thought of and said about what are the, like, what aspects of intelligence are being embodied by those fancy equations in my Excel spreadsheet. Can this thing do math better than I can? Probably. Can I locomote through my world better than a smart speaker? Absolutely. My sensory motor decision making is much more enhanced than say a toaster or a smart speaker. So I'd like us, again, this is my pitch to everyone when we talk, especially when technological personnel begin to speak to medical personnel, people who are trained in both these fields, being able to ground those discussions in data, in decisions, in goals is going to be incredibly helpful for demystifying the artificial intelligence and instead saying, what exactly is this technology trying to achieve? How is it actually acting upon that world? What is it perceiving? And what decisions is it making? These are really great questions. And I'd like to dispel that misconception that really intelligence is either an A-B thing or a line. And then it gets really scary to think about applying artificial intelligence in a field like medicine, if it is really just a binary distinction between intelligence and not. Okay, so I'm going to take a break to sip my tea, and I can't ask for questions right now, but we'll table those to the end. So you might be asking at this point, well, why machine intelligence? We hopefully have seen that machine intelligence is beginning to play a role in things that we might see in the clinic or things that we might see in our daily life. We've hopefully been able to now define intelligence and artificial intelligence, and also then begun to deconstruct that into the hallmarks or the field marks of intelligence in a way that can facilitate our decision making. But then the next question is, well, why should we care about this? And I usually boil that question down, the answer to that question down into three things. One is that machine intelligence is something that we seek to create because it gives us enhanced control over this changing and increasingly complex world. Especially right now, I think this is a very apropos point. Another is that it does something that I think our species has tried to do since the dawn of us being a species, which is to peer into the future. Anticipate future events. This is, in some way, people seek machine intelligence as the crystal ball that lets us say what's going to happen tomorrow, in 3 minutes, in 2 years, with respect to the stock markets, our bodies, the environment around us. So it gives us the ability to anticipate future events based on learned patterns of the past. And also, machine intelligence really gives us general tools for solving very hard problems. Because of this, we've seen machine intelligence applied in all sorts of settings, controlling complex systems, extracting knowledge from massive amounts of data. This is happening almost certainly right now as we're communicating over digital channels. And in terms of how our information is being compressed and transmitted. And there's examples in finance, healthcare, energy, resources, transportation, information processing, that machine intelligence is being used to in fact, give us better ability to interact with the world around us. That's why people seek machine intelligence. And so this, normally I would have showed you a video here, but I think I can just paint this picture with my words, is that this is my ex-student Gotham Vasan, since went on to Kindred Systems, but he's shaking hands with the modular prosthetic limb that's based in the Smart Network in the Blink Lab. And when Gotham was shaking this robot's hand, it was the most stilted handshake I have ever seen. Like, imagine seeing like this awkward, clunky thing, and then the robot was like fighting him. It was like this really awkward handshake. And I'd like to ground the next little section of my talk in this failed handshake, because it really highlights the importance of learning. So we talked about why machine intelligence, but we might then ask, why machine learning? Why should we actually care about a machine that not just has the properties of intelligence or hallmarks of intelligence, but in fact begins to change or adapt, begins to learn from its experience with the world to better embody some of those hallmarks of intelligence? And one of the reasons is that we might know what we want to achieve as designers of a technology or the people that are implementing a system, but we might not know how we want to get it. I might be able to say, yeah, Gotham gave a great handshake to that robot arm and it gave a great handshake back. But as a computer programmer or as an engineer or as a designer, I may not know how to, in fact, program the arm to do that. Learning allows the system to fill in those gaps. Another is that things are complex. Like, I might actually, as a designer, know how to program a really great robot handshake, but to actually do that practically might take an astronomical amount of time. And by the time I've done it, the systems might no longer be the same, or Gotham might not be the person it's shaking hands with. And then we'd have another extremely long amount of time to re-engineer a system. So learning in one way allows us to scale up to tasks that we know how to solve, but that are incredibly complex or intractable in terms of the time and energy it requires to solve them. And also, things need to adapt. Systems do need to adapt. Once they're deployed, a system is already in an environment that it was likely very much not designed for. So things do change in the world, and learning allows systems to adapt or to change or to compensate for changes that happen in the environment around it. Okay, great. So this gets me to maybe one of the two sort of high-level bullet point slides of this particular talk. And right now I'm going to take a step away from the definition, step away from the sort of the motivation for machine intelligence and artificial intelligence, and now speak to how, in my mind, this is my deconstruction of this particular impact set for AI and machine learning in medicine, to three main ways that, in my mind, AI is beginning to transform medicine and is seeing utility in medicine. So again, this is one of the, if you walk away with one thing, you can just cut this slide out and walk away and leave now. It's great. And that the first is that AI is able to begin to help us understand populations of patients, populations of people. This I'd like to call generalization. This is just one way to name this, but to understand populations. Another is that AI in medicine allows us to begin to understand individuals. I'm going to call this personalization. And third, that with respect to that generalization and the personalization, the way that whole populations behave and individuals behave within those populations or relate to those populations, we can now think about AI and machine learning in medicine as helping us choose or improve interventions. I'm going to call this optimization. And now, again, in the field that I'm more familiar with, something like physiatry, by connecting patients to assistive devices, that's one way we might see optimization manifest. We might also, by other ways, such as by helping deploy treatment strategies or customized treatment to individuals. A lot of the work in precision health and personalized prescription might fall into this kind of category of optimization. So with those, I'm just going to go through that one more time because I think this is one of the important slides of this particular talk, is that AI has and can be applied in medicine to help us understand patient populations, to understand the individual, to understand individual patients, and to help choose and improve interventions. So for the next little bit of the talk, I'm going to go back into exciting video and image mode to be able to show you and ground some of these ideas in what's currently being done and some of the recent work that's happened in, say, the last 2 to 3 years. The first example I really like, and it's partly because it makes such pretty pictures, is the Human Connectome project. For those of you that are not familiar with it, this is a project to begin to map the flow of information through the brain, the way that the brain connects to itself, the inherent structure in the brain. And I like to use this example of both personalization and generalization because we could think about seeking as a community to understand the operation or the structure of the brain. This isn't like my brain or your brain, but it is the structure of the brain, how in general regions of the brain connect to each other and pass information. So this is an admirable goal and something that machine intelligence and intelligent system technology is readily able to begin to support. We can also think about personalization, where we try to understand the way that an individual's brain is wired or connected, and then relate that to the general trends that we have extracted from massive amounts of information about how brains in general operate. So I like to use this particular example. Another example that we might imagine is that this is just one of treating diseases of the eye, but that we might seek to train large machine intelligence systems to begin to diagnose retinal disease, and to do so with an accuracy and less errors than clinicians who've been in the field for decades. So to do this, we might have to understand what the eye should look like, what the interior of the eye, what all of the different aspects that we might measure of the eye should normally look like in general for different populations, and then relate the information of an individual to those general trends. So that's another example of how we might begin to think about both the generalization and the personalization, the understanding of the population and understanding the individual, and then connecting the two. With respect to optimization, I think this is one of the areas where I see the greatest potential for transformation in the very near future. Right now, I'm showing you one of the examples that is probably on many of your minds if you've seen some of the recent releases from companies like Neuralink. But we're starting to see a step change in our human ability to deploy machine interfaces into our central nervous system. This is from the again from the Neuralink white paper that was released back in 2019. There was a recent 2020 update just a little while back. But the idea that we might now be able to, in a bidirectional way, implant hundreds or thousands of electrodes directly into the central nervous system in a very non-invasive way, as almost an outpatient procedure. This is something that is very transformative in terms of tightly coupling humans and the machines that support them in their daily life. For those of you that aren't familiar, I just will highlight it. Like literally, Neuralink has built a sewing machine that can begin to sew flexible electrodes into the surface of the brain while missing things like blood vessels. So the idea that it might, in fact, auto-trypan, much like LASIK eye surgery, that you could go in an afternoon, have a piece of your skull removed, have a sewing machine, sew electrodes into your brain, and then have everything capped back off again. You have a little USB-C connection, so you can actually plug into that. And they're showing that those USB-C connections actually have some very spectacular results in terms of the density of channels. It's not just Neuralink. There's other companies that, like Paradromics, that are looking to put 10,000 channels per square centimeter into the human brain. And this is just spectacular. Again, I'll just highlight this, like literally the Neuralink stuff is actually a sewing machine that sews into the brain. I don't know how you feel about that. I think it's kind of wild. There's also the attempt to not just interact directly with brain tissue, but to do things that were also considered very miraculous previously. I'm just showing you a slide now that relates to a collaboration that the folks down south of the border have with Intel AI to create neural bridges, to create technology that in fact might just completely bypass a section of damaged spinal cord, and to be able to essentially automatically reconnect through digital technology both ends of that damaged spinal cord, using Intel's AI technology. This particular grant, along with DARPA, is looking to continue to, I think, scale up this to be able to bridge parts of the human nervous system in ways that's never been bridged before. We're starting to see, and this is the Osteointegration work for those who have not seen it. Right now I'm referencing specifically the work of Max Ortiz-Catalan, and the idea that we not only can now connect a device to the outside of someone's body by way of electrodes, but that we might be able to integrate those devices, especially a prosthetic device, directly into the bone structure of the human body. So the person is mechanically and physically coupled to their device, but then also begin to run wires through that coupling, such that a device, an assistive technology, can now be integrated with the muscles and the nerves, that it can sample information from the inside of a residual limb, pass that to a robotic device, and then also pass information back into the nervous system of the person. This is a tightly coupled, true electromechanical interface that would have truly blown the minds of the early cybernetics researchers in the 1950s and 1960s. This would have just been something that seemed beyond all conception at that time. I'd be remiss with not mentioning something that is the perhaps next step of telemedicine and telepresence, is that there are many companies now around the world which are looking at ways to create avatars, things that people might project into, everything from, say, the double robots that maybe some of you have used and driven around to interact with patients, right through to being able to project yourself into another body in a very, again, a tightly coupled way. This is also something that is on the horizon, and on the very near horizon, that was not possible before. I'd be remiss, of course, in not mentioning, I like talks where I can talk about other people's work, because there's just so much exciting work that's being done around the world. Right now, I will zoom back in to talk just for 2 slides about what we're doing in the Blink lab. This is the lab led by Dr. Jacqueline Hebert and part of the SMART network here at U of A in the Department of Medicine. And we are looking at things like osseointegration. Jacqueline's done a spectacular job of bringing osseointegration here to Alberta, so we can begin to actually try out some new things with regard to how humans and machines interact, not only from a very practical perspective, but also to look at transformative forms of machine intelligence, especially machine intelligence that adapts and evolves alongside a user, and to begin to look at how people might actually change their behaviors or improve their behaviors with respect to different forms of intelligent prosthetic technology, specifically looking at gold standard ways to measure the outcomes, to measure and to quantify the interactions between a person and their assistive device. So it's not just that we're starting to see that we're able to interact and engage new kinds of technology with the human body. We're also seeing that we are now able to measure the interactions between a person and machine in a way that we never have before. So we can truly understand the fundamental principles of a person especially someone in a medical context or a physical medicine and rehabilitation context, truly measure the way that changes in the intelligent systems technology they use in their daily life changes their behavior, their ability to meet their daily objectives, to meet their goals and their functional needs. So this is something that is also very, very new. And I showed you those examples in part to sort of ground the idea of personalization, generalization, and optimization. In those last few examples, you can see very much how machine intelligence can begin to optimize a particular system to an individual. There's no two people that will have exactly the same osseointegrated setup. There are not two people that will have exactly the same set of electrodes implanted in their spinal cord. The systems themselves have to optimize to individuals. And our analytics, our assessment technologies, our outcome measures also have to optimize, in my opinion, to individuals. But I used all of those examples as well to motivate this particular slide. This is the second bullet point slide. I could say, take this and walk away, and now you're good. And that as we look forward, I do truly believe that we're looking at a case where we have very complex bodies, and that is going to entail multidisciplinary care in a way that we have never seen before. And the main statement here is that if we can imagine that a patient's body and a patient's mind are comprised of both biology and technology, how do we best treat the whole patient? I'm going to say that again one more time because I want to emphasize that it might be that a patient's body might be comprised of both biology and technology, and that a patient's mind, indeed, the way that they affect the computational part of their ability to achieve goals in the world might also be comprised of both biology and technology. And maybe that's already the case. I mean, we all probably have these smartphone things we keep in our pockets, but that if that is true, then how do we treat the whole patient? And it is very, very likely that patients may and will increasingly consider the technology that they use to be part of themselves. If anyone ever tried to hit your smartphone with a hammer, I think you'd start to see the glimmer of this. The idea that biology and technology might also not be easily separable, and that you just can't remove technology from someone's body. It's very, very hard to think about just removing the technology that is, say, the long-term memory consolidation module that is part of someone's brain, or the neural interfaces in the peripheral nervous system that are allowing them to connect to the device that they use as part of themselves and embody as part of themselves. And so maybe the way that this will change things, maybe it's the way that this will start to transform multidisciplinary care, is that in a way like never before, normal care may soon, in fact, involve experts in, of course, things like tissue and muscles and nerves and bones, but also experts in hardware, in software, in data science, someone who can flash the firmware of that myoelectric prosthesis someone's wearing, or someone who can actually go in and rechange the surface properties of an electrode on the fly that is implanted in someone's body. That normal care may seem to be even more multidisciplinary. I'm thinking like the wonderful, like the hip and knee clinics and things that already involve many practitioners coming together. I can only see this increasing with technical personnel working alongside the already diverse group of clinical practitioners. So I'm going to close. We're almost at the very end of this talk and we'll have time for questions. I just want to show you, just in case you're wondering what the robots are up to these days, I'm hoping the video is not super choppy as you're seeing it on your end over whatever bandwidth you have. But you can see now that we have mobile robotic systems in the world that are doing spectacular things. They're doing things that, well, let's see, we'll wait till the video does the next bit here. Right? They're doing things that arguably I have a lot of trouble doing. So the robots are, in fact, the robotic systems in the world are, in fact, advanced to a point that was also fantastical, even at the end of the last 100 years. So why did I show you that video? I showed you that video because partly, oh no, we're in the blooper reel here. Let me get to the next one. There we go. I showed you that video in part because I've largely neglected exoskeletons throughout this talk, or robotic systems that are attached to the outside of someone's body to support them in the way they live their daily life. And if you can see this video, these are individuals that are using a suit by a UC Berkeley spin-off company. But exoskeletons are robotic systems that are attached to the outside of our body. Now couple that in your mind with the robotic system that you saw in the previous video. I'd like to make the point that it's not that we're waiting for robots to get better, and it's not that we're waiting for humans to evolve. It's that there's something missing in the way that humans are interacting with our technology that we need to treat very seriously to be able to leverage the full potential of all these other, say, robotic technologies and information processing technologies we have in the world. This gets me back to the slide that I said was one of the most important slides from earlier on, which is that machine intelligence is that glue. That is the the missing element is advances in machine intelligence, advances in the intelligent systems technology that connect all of those signals flowing to and from the human body to all those signals flowing to and from an assistive machine. Machine intelligence is in fact the glue, an advanced computing technology that will begin to connect these two parts together and allow, say, someone using an exoskeleton to begin to exhibit some of those abilities of that robot doing backflips you saw on the previous slide. But it's more than that, in fact. I really think that it's not, I've grounded this entire talk in someone connecting to an assistive machine, but really machine intelligence is in fact the glue that allows us to connect the human mind to the diverse world around us. It allows us to extend ourselves out into that world, to better perceive the information in that world, to be able to better act upon the wild, squishy, complex world around us, and to better think about or make decisions within that world. I'm driving it back here to data, decisions, and goals. And that this isn't just something that we might imagine being applied to someone like a patient using an assistive technology, that this is a way we extend our abilities as patients, as caregivers, as policymakers. Machine intelligence is in fact the advanced technology that unlocks a whole new form of decision-making and a new power of decision-making that allows us to personalize, to generalize, and to optimize in ways we never have before. So with that, I'm going to close like 1 minute over time. I almost did my job properly, and hopefully we'll have time for discussion.
Thank you, Patrick. That was amazing. I'm going to start actually while people are typing in their questions in the Q&A and the chat box, and just start by asking you, where do you see, there's a lot of things related to our smartphones you talked about, and apps that we can download and things, ECG technology, even some radiology technology. How far do you perceive we are from having that independent patient point of contact ability to do very advanced diagnostics and some of the things that are already available, but being used in a meaningful way, going live. So in other words, I think it was in the Q&A that somebody asked, when are the radiologists going to be out of a job, right? What do you think are some of the barriers to bringing them to prime time?
Oh wow. Okay, so I'd like to do the. I know that I've heard people claim live in presentations, machine learning experts claim that well, we should stop training radiologists. I firmly and adamantly disagree. I think that we need to change how we train people who use technologies. But that this goes back to my last slide, and I think this is maybe the meta point, is that in fact we see technologies improving our ability to make decisions all the time. If you can increase the window into the world or into the decision-making space that you have, if you're trying to make a decision about a patient, and you've only seen in your clinical career, you've seen 3 cases, and now imagine you could have something like you could just query and say, well, okay, there's been 10,000 cases in the entire world. How does this is the personalization and the generalization. How does my new individual relate to the 3 patients I have seen before, but then also to those other cases that have happened? Where are the similarities? Where are the differences? What were the outcomes? How can I begin to optimize the treatment for this new individual based on that knowledge? But it isn't actually removing any of the decision making. It's augmenting and supporting the decision making of a medical practitioner. So when we say hey, radiologists are going to continue doing amazing radiology like things, but is it going to be exactly the same thing? Probably not. Are they going to be better trained at using advanced technologies that help them see patterns they could never see before? Probably. Could you potentially someday hold a 4-dimensional model of a radiology scan in your mind and make decisions based on it? I don't know if any of you can visualize tesseracts or 4-dimensional objects. Probably not. I'm guessing there's gonna be a lot of people whose eyes just started bleeding right now trying to do it. But there is a world where we could imagine supporting our say a radiologist and being able to see a data space that was never possible before, where you can overlay multiple forms of data and actually visualize that and make decision on this space in a way that was previously very uncomfortable or impossible. So this extends back out, and I think this is where I can see, both for practitioners and also for patients, being able to have technologies deployed in ways that are both immediately practical and also in ways that are going to be a step change in how we deliver care. Well, it's that we can take the gold standard, whatever the current practice is, and we can start to see ways to incrementally improve that gold standard. That's very, very good. The way to have something that in fact makes that step change from gold standard very large is, I think, to view this as a process of augmentation. That was my last slide, and I think that is in fact the way that machine intelligence does help us. And it's going to be, surprisingly, this is my hypothesis, a weird sort of reverse translation path. Like often we see things that are developed in the medical realm that become like consumer grade electronics, like bioelectric sensing apparatus. But we can also see that there's a lot of technology being developed in the consumer arena, which can reverse translate back into the medical domain. I even think of early on how people were using the Connect, or like those 3D depth sensing cameras. That was like a gaming device. A lot is being done in the gaming industry, like even for things that might benefit telemedicine, that can now start to be translated over into a medical context for like a huge amount of efficacy, but with in fact a lot of already rigorous debugging of how these technologies play out when they're being deployed. So I do think that there's going to be a very nice pathway from consumer grade technologies into medical grade technologies that allows us to see the benefit of AI, because it's already being used to support so many other services and things that we do in our daily life. And I'll be seeing the opportunity to apply that to the medical field. That was a really long answer.
That was great. Thank you. There was a question around COVID, of course, and application of AI within COVID. So, in terms of prediction I guess I'll just simplify it in terms of the question that was asked. How do you think AI could have made an impact, or could make an impact within the COVID world with regards to prediction or treatment or any of the other things that you've covered today?
So again, I'll give one example, and just again acknowledging my COI that I have a DeepMind hat as well, is that that protein structure prediction is something that AI has been able to do to essentially estimate the structures of proteins that make up COVID, and allow people to begin to potentially build better treatments or to better understand the functioning of this particular little beastie. So that's one. I'm just using that as an example. I said with my DeepMind hat, because that's DeepMind open sourced some of the protein structures that were generated by one of the neural networks that looks at protein folding within that DeepMind has. So open source protein structures, the ability to actually understand the functional structures of molecular machines, that's something that in fact AI is very well placed to help us do. Another piece that I think is really interesting, and this is taking my hat off. Another really interesting thing that I think we can leverage is that prediction based on localization is something that's really hard. Like if you have all sorts of diverse factors, like where exactly something is, how small minutia of like local weather and local city structures plays into the existing case counts, machine intelligence, this is both a sort of a personalization and generalization kind of situation, is that it has the ability to fuse many diverse data sets into a decision-making model or into a predictive model. I'm even just going to go to like, you have perception. Can we perceive all of the data streams that are being generated by our species? Yeah, we're doing a great job of that. Like now we actually have more access to the data streams being generated by a species than we ever have before. So given that, can we start to build predictions about how those data streams will change? And the answer is yes. And the models, the machine intelligence systems that we have to begin to make predictions based on that perception of our species is in fact increasing as well. So even just thinking about like, hey, how will like case counts change in Lethbridge? Is it something that we say, well, this is how Canadian case counts are changing, so we're just going to apply a baby version of that to Lethbridge? Well, that's crazy. Lethbridge is different. There's everything from weather to population to the way people interact to how they work to what they think to their social structures. So being able to start to think about general trends, and then how those, like knowing how diseases unfold, knowing models of disease progression, like mapping that to localized circumstances is a place where AI could actually have a significant impact. And like there's tons of people around the world that are doing this. Actually, a few of us from U of A and other words and other places are editing a special issue of a journal on sort of how AI can be helping with non-critical COVID situations. And so that's something that like, it's neat. I've been watching papers come across my desk saying all sorts of really cool things. And so I do think that sort of generalization, personalization link done on a regional or a local basis is one area where we can start to leverage that massive amount of information that we can perceive about our society. And then also then start to figure out the forecasts of case progression in any given area. And of course, this isn't just for COVID. This works for other diseases too. It's just, this is a very timely one.
Thank you.
I hope that answered. As I was putting, thank you. I hope that answered your question, at least in part.
We'll keep an eye open definitely for that. So I think there was a question from related to mental health and psychiatry. The question was around if you know of any AI and machine learning applications on the mental health and psychiatry horizon.
I sure do. And I don't know if Russ is on the call right now. Our very own Russ Greiner, another Amy Fellow and a professor in computing science, is looking at AI and machine learning for psychiatry and for mental health concerns. There's some really cool work that was subject of a few really big news releases at U of A. So I would definitely defer. I won't even try to speak on it right now because I think Russ is the right person. If Russ is on, Russ can't be on the call right now to chime in, I don't think, because it's a panelist mode. But I would definitely say yes. And in fact, University of Alberta is leading the charge in that particular area with Russ Greiner and colleagues doing amazing things in that area. But I'm not the right person to talk about it. Russ totally is.
Thanks. There's a question around, some of these technologies require facial recognition, and there is, some things that we're already well aware of that require facial recognition technology. So there's a question around what are the privacy implications of the things you're talking about, and can we mitigate those concerns?
So I will have a disclaimer as well that I am, in fact, not a privacy specialist. So I would defer to my colleagues who actually do exactly this as their career. It's really awesome. And there's some very smart people, including those that we have here at University of Alberta, that are thinking about exactly this. I will sort of zoom out a bit from facial recognition because I realize that's a topic on everyone's mind. And especially probably some people saw some news reports recently about facial recognition in malls. But the question to be asked, I think, goes back to data's decisions and goals. What data are we comfortable? So it's partly like, what data does a system, an intelligent system technology, what data does a system use to make decisions in service of the goals? Are we aligned on those goals? That's a very important question to ask. But then the other question is, well, what if we believe that a system is trying to achieve the goals that we have set out for it, and we also, let's say, even believe that the decision-making being done by the system in service of the goals is something that we are okay with, what data are we okay providing to a system so that it can make decisions to achieve our goals? And now, this isn't just facial recognition technology. I mean, I really, like, we all have these phony things I was saying earlier. Mine now forces me to put my face up to it to unlock it. I really liked when I could use my thumbprint, but that was a choice. Like, when I'm lying in bed without my glasses on, there's no way it's recognizing my face. When I'm like, oh, do I have to get up for the Department of Medicine seminar right now? And so I'd rather be able to give it information about my thumbprint to allow it to privacy unlock and open up my calendar or my alarm and turn off the alarm. Someone else might be not comfortable with having that particular set of information from their body being recorded. Would someone be very comfortable with a technology having access to their genetic code or to the makeup of chemicals in their bloodstream at a moment-by-moment basis? If you're someone who needs, say, insulin and needs to monitor their blood levels, then yeah, you might be comfortable providing that information to a machine, because that machine's goal is to keep you alive or to keep you healthy or to keep you able to function in daily life or to alert you to problems. So you might be very comfortable. I don't know if Giovanni's on the call at all, but thinking about how you breathe and how you interact with the world in your respiratory system, would you be comfortable giving information about your heart rate, your breathing rate, and other parts of your body to a system that was helping to, say, alert a medical practitioner that you might be having an incident that was going to be very, very dangerous to you? You might be okay with that transaction of, yes, this data is okay, because these goals are important to me, and because I believe that decisions made based on those data are going to be reliable to my satisfaction. This is saying something about trusting the decision-making process, which is something that a lot of people, if you think about AI as a black box being applied to a problem, it's really hard to build up an understanding of trust. If you break it apart into pieces, and I just proposed perception, prediction, and action, and data decision and goals, but break it apart in whatever pieces you want, to understand those pieces and to trust each of those pieces, then says, do I trust my data going into those pieces? So I think that's the right view for this. And it's a case by case based on each of the potential systems and goals they might have as we start to dissect the technologies used in our daily life. A one size fits all approach, maybe it's going to be hard for everyone to trust that, because we are unclear about the goals, we're unclear about the decisions, and we might even be unclear about what data is being sampled. That's a case where there's so much fuzziness that it will be very hard for you to say, yeah, I'm okay with that, and I'm okay with the privacy implications personally. And then we have, of course, there's policymakers, there's us as a species trying to decide, what are we okay with? And that's another very active conversation that that is definitely being had, but it needs to continue being had.
I'm really cognizant of the time because I know Patrick has to run at right 9 o'clock. So on behalf of the Department of Medicine, Patrick, thank you so much for a really thoughtful and inspiring talk. And Patrick has assured me that he's okay with people getting in touch with him because we were hoping that this would stimulate a lot of questions and a lot of thought about how AI can be applied within your areas. And so hopefully you won't get too bombarded, but he's told me in the past that he's open to talking to folks and you know, just going forward with great things to come. So thanks, Patrick. Just for everyone, once again, next week we do have a COVID centralized talk where we've got Dr. Stephanie Smith, Lenora Saxinger, and Robin Harrison back next week to talk about sort of where things are going with the second wave. So once again, a reminder to get your flu shot and please stay safe. And thank you for everything.